Okay, folks, so we'll get started there. And at long last, we're starting on neural networks. I had to drop one or two shorter lectures that I had included from the originally from the beginning of the year that I kind of felt I wanted to get started on the neural networks and get into that and try and get a bit more done on that. So that's why those one or two got dropped. What I dropped was PCM, which is Principal Component Analysis, and I also dropped the some of the I wanted to cover one or two unsupervised techniques, so I had clustering there. If I ever get a chance, I'll do a bit of a recording on them as an extra, but certainly they won't be included on this course in order to try and get ourselves onto the maybe more important stuff on the neural network. So that's why I've kind of jumped forward to that. So we're going to look at neural networks tonight. There's a fair bit in tonight's lecture, so we'll get moving on it. So what are neural networks for? So the machine learning algorithms that we've looked at so far are extremely useful and should be the first option you look at for any problem. However, when the number of features goes up and the problems become much more complex and non-linear in their nature than the previous algorithms that we've used, such as logistic regression and SVM and those sort of things, or decision trees, they can struggle to cope at that point. So in these cases, neural networks can be very, very useful, and that's where you should use them. Now, it may seem, particularly if you listen to the rhetoric around machine learning and deep learning at the moment, or certainly over the past few years, it may seem that deep learning neural networks or deep neural networks are the only game in town. But that's not the reality at all. And particularly, it's not the reality when it comes to actually building systems that you're actually going to deploy and that you know are going to work properly and reliably. So what I would say is that that idea is a mistake. It's certainly the big area in terms of research, but not necessarily the only game in town when it comes to actually working with real systems. So you should always use the simpler algorithm if it will adequately solve the problem. So don't automatically try and solve every problem with a neural network if that's really too big for the problem that you're trying to solve. Okay, so that's something to be aware of. Simpler algorithms, they use less resources and they usually have greater causal reasoning. And this is a term that you'll see come up as a recurring theme throughout this course, this idea of causal reasoning. The idea that we can determine what has caused the particular output that we have and been able to work our way back, and that turns out to be very important. We saw with the decision trees in particular, they were very easy to do causal reasoning on, and the reason for that was because they were so logical in their nature. Just disappear for a second. I want to get a mouse here so that I can keep an eye on my lecture monitor there in the background. Okay, so this particular data set, which you may have come across, is called MNIST, and it's basically a lot of small little images. They're only 28 by 28 pixels, and they're in grayscale, but you could almost look at them as just being binary, black and white as well. But I think they're normally given as a grayscale value so that you can see kind of edges on things. And basically what they do is they have just these digits, so 0 to 9, and they were particularly useful when it came to training neural networks for recognizing handwritten digits, so for things like zip codes and so on. Okay. And generally speaking, if you're going to do some hello world, or if you're going to do some deep learning work, this is kind of the hello world of deep learning. So you can set up a neural network that will fairly quickly train through these. With modern hardware, you should be able to train relatively quickly. So you can set up your own network and actually build something like this to train and get fairly good accuracy up at the 99.7%, and it would certainly be relatively easy. I'm not sure what state of the art is currently on MNIST, but it's got as far as it really needs to go. But if you consider the problem, each sample is a grayscale image of 28 by 28 pixels. Now that's 784 features, and the problem is a highly nonlinear problem, because if you think about just determining from pixels, even if you look here at the positioning in each of the cases, the ones are in different positions on each case, the zeros, they're different thicknesses and so on, all of those different things, and yet we can quite easily as humans recognize these as the different digits that they are. There's a 5 there that might throw a few people. So you can see the situation here where this is a very non-linear problem that we're trying to solve. Go from pixels all the way to determining what number that we're dealing with. So imagine trying to find a hyperplane, which is basically like a line except in higher dimensions. So a hyperplane in 784 dimensional space, because that's how many features you have now with all of your different pixel values. You can see how that would be very difficult, and you'd need those hyperplanes separating each of these out so that you got all 10 numbers. So you can see that if we try to do this with something like SVM or logistic regression or things like that, this would be a very difficult high dimensional non-linear problem to try and solve. So the only way you could maybe try and do it is maybe have some sort of a polynomial model rather than a simple linear model that then goes into your logistic classifier. But if you try that, what you're going to find is that you're going to have it fairly high degree polynomial in order to kind of fit the shape of the system that you're going to do. And the problem with that is that you've got so many features, and each one of those features has to have, squared and cubic features, and those multiplied by each other. You're going to end up with a very, very difficult model to try and deal with. So in cases like this, it makes more sense to try using something like a neural network. Now basically what the neural network does is it tries to do all that maths combined within its neural network. So it is actually made up of quite a lot of nodes, and it is generally quite a big system. It's just that we don't need to think too much about the model. It tries to learn the model itself. So the neural network is made up of these perceptrons, or sometimes known as artificial neurons, although I think, as I've mentioned before, most people who deal in neural networks would prefer to stay away from the idea of an actual physical neuron and making the kind of they make a very clear distinction that they're not really trying to copy what goes on in the brain, because we don't really know what goes on in the brain. We're just trying to come up with an artificial mechanism for doing this. And so we have a fairly simplistic system here where we have some inputs, x1, x2, x3, and we of course could have more than that. Each one of these is multiplied by a weight, and oftentimes when we draw these diagrams we don't even show the weight, we simply show that as the line. We'll see some examples of that in a moment. We sum all of these things up, so that's what the sum symbol, the sigma or sum symbol, is there for. We usually add a bias of some description, and the bias normally does not go through a weight, or better to say it actually is a weight of its own. But what I mean here is that it isn't multiplied by some input. And then what we do is we pass through an activation function after we've done this addition. Now this activation function is vitally important. It's a non-linearity. So non-linear. And that's important because what we do is we introduce these non-linearities into what is effectively, these are linear algebra operations that we will be doing here, where you're taking a vector and you multiply it by this vector here. So that's very much just linear algebra there, but then we have to apply a non-linearity to it. And the reason that we need to apply non-linearities to it is it adds complexity to our model. So our model is then able to act in a much more complex way than it would have done previously. If we simply tried to do this with a linear model, the chances are we would never be able to model the non-linear nature of the problem that we're trying to deal with. So if you want to solve a non-linear problem, you really need a non-linear model in order to solve it, and that's where the complexity comes in, and that's why we need these non-linear activations here. This idea here, it might look complex, but it's actually relatively simple. And indeed, if you consider something like your own exam marks, this is relatively easy. So I think most of you guys are doing three modules this year. You're doing the machine learning with me, and you're doing some of you are doing the maths, maybe the linear algebra module, and you're maybe doing the ADAS basics. And each one of these, as it happens, are all weighted the same. So the weight would be 5 credits in each one of these. What you would do is you would multiply whatever mark you get by the 5 credit weighting, add up the total. There's no bias here. The bias would be 0. If there was a bias, it would be suggesting that we start you off with maybe 20 marks, which we don't. And of course, what you then do is you calculate your output. There's no nonlinear activation either in that particular case. But you can see here that if we just added a nonlinear activation onto it, that's effectively all we're doing. So these are very simple operations, and this idea of the, multiply this by this and then accumulate it into an overall value, that is what digital signal processors and particularly GPUs for graphical processing units, that's what they're good at. They're able to do millions of these per second. So millions of these accumulates per second in order to do the calculation. The actual nonlinear bit is actually much more computationally intensive for it to do, but it can do vast numbers of these in a very short amount of time, and that it's built basically to do this sort of operation. Okay, so the thing is that this generalized perceptron here can actually be used to do many of the things that we've already seen. So for example, if we look at the actual function that's taking place here, and this is our nonlinear function here, and we haven't specified what it is yet, what we do is we multiply the weights by the weight vector by the input vector and add a bias there. So w by xi plus b, we sum them all up and then we do some function on it. Okay, so this is effectively, if we were to say that this function was a sigmoid, then what we're effectively dealing with here is the logistic regression function that we did previously. So if we look at the mathematical form of the perceptron, it looks as follows. We can see that the part inside the brackets is a simple linear model. Now if we set f to be the sigmoid function, you can see that we have a logistic regression classifier. Do bear in mind though that you still have to undergo all the training. So in other words, we haven't actually set these weights yet, and just like the logistic regression, those weights have to be set. So this is going to be a simple linear model, so we're going to obviously they're effectively going to be the different slopes depending on how many dimensions it is, and we have to learn those in order to actually learn our model. So so we have to train that with an appropriate loss function to set the weights to the correct values to make it useful as a logistic regression classifier. The output y would be a probability, and I've, for no reason more than I just want you to be used to the sort of mathematical formulation here, and I think I've shown you these probabilities before. But one little thing that we've added extra here is that what I'm saying in this particular case is that for my sample I, my label yi is equal to 1 given. So in other words, we want to find out what's the probability that the output of this is 1, given that we have this input xi, and that's what that straight line down the middle means. So what we're saying is yi is equal to 1 given xi. So what's the probability of that? And the last bit here with the semicolon and the w, that means parameterized. So it's parameterized by w. So what we're saying is, what is our probability of yi equaling 1 given xi if we're using the weights w? Okay, so that's the overall scheme of what that's saying. And the probability of it being 1, there, if we want to find out what the probability of it being 0 is, we say the exact same thing, but what we need to make sure is that if we're dealing with just a binary system here, that we take whatever the chances of it being 1 away from the value 1, so that gives us the rest of the probability. And what that says is that it either has to be a 0 or a 1, and in terms of its label. So therefore we say if whatever the probability of it being 1, the rest of that probability must go to it being 0. Okay. Now we could also make SVM with a single perceptron as well, and so the same is the case for linear SVM, not the kernel versions admittedly, but again we can do all those nonlinearities too. So we just changed the activation function, and instead of the function that we used here, which we said we were going to use a sigmoid, instead the activation function here, we use something like a hinge loss, as we call it, which is basically the kind of SVM idea here, where if you're over 0 and you've added some margin here, and remember when we worked in SVM, we worked with just a margin of 1, and because that was the identity for multiplication, we could effectively have a margin of anything we wanted. We could decide it from there. So again, we can basically turn we can turn our single perceptron into SVM simply by coming up with the appropriate loss function in order to figure out how it's going to work. But let's look at some standard activation functions that would be used in neural networks, because of course there's very little point in us using a neural network and then just recreating something like SVM or recreating something like logistic regression. Very often, by the way, on the very end of a neural network we will do something like that, but in the intermediate layers it makes very little sense to be just reproducing those, given that we already have good systems for doing them. So let's have a look at some activation functions. I've only mentioned 3 of them here. There are a good number more than that, but I obviously want to have enough to get through the lecture. So the tanh function, which is the hyperbolic tangent, and you can look this up in any maths book or try it even in Excel or something like that to see the response of it. Basically what happens here is that it's a constrained function, so it kind of squashes everything into the range, the output range -1 to +1 here. Okay, so no matter what input we put in, so I could have an input that's way over here, then that is going to get squashed, as you can see, to -1. And if I have an input way over here, that is going to get squashed up to +1 there. And we kind of tend to use that word squashed because we squash it all into those values. So the tanh activation was popular in the early days of neural networks, but has somewhat fallen out of favor of late. Its pros are that it is symmetrical, first of all. So we have this symmetrical thing around 0, so that's good. And it basically means you have a 0 mean from it as well. And it constrains its outputs to a manageable range of -1 to +1. However, the saturated sections can kill gradients. So the problem here is that if you have 2 values here, okay, so let's say there are 2 values there and we want to calculate the gradient of them. So you have an input, let's say, of 3 and an input of, say, 5. And they're both there and there. You can see that they're almost the same value there, okay? Because they're almost the same value, then the loss associated with them would be almost the same, and therefore we wouldn't learn anything from the differences between these 2 values once they go beyond a certain point, okay? So while this is a nonlinearity and it adds that extra complexity that we want, the problem is that we sometimes mightn't get a gradient, and we really need a gradient because we're going to use gradient descent in order to figure out how to find the bottom part of this function. And if we have to move through this activation at some point and its gradient comes out as 0, then we can't get past that gradient all the way down the rest of the network either. So we learn nothing at that point, and we can't pass it further down the network either. Okay, so there can be all sorts of problems with our gradient disappearing effectively, and we want to try and watch that. So therefore tanh started to fall out of favor, partly because of that, but also partly because of the complexity that it takes to do it. The sigmoid function was regularly used as well. It's another nonlinearity. Looks very like the tanh, except the only real difference is that it goes from 0 to 1 instead of -1 to +1. And of course this was particularly useful because numbers between 0 and 1 are where probabilities lie, and therefore the sigmoid was going to be great for modeling those probabilities, and we would, no matter what values we got in, we would squash them to within the range of probabilities. So the sigmoid nonlinearity was very popular, as it was also believed to be a good analog for the firing rate of biological neurons, and it constrains the outputs to the range 0 to 1, which is perfect for modeling probabilities. However, it's not 0-centered. As you can see, it's up here at 0.5, so it didn't have a mean of 0, and they didn't like that so much. So that was one of the problems with it. And for that reason, the gradients will all be of the same sign, which is kind of problematic as well. I don't really go into the details of why this happened, because in many cases what occurred is this happened back in the earlier days of deep learning, and they just moved on to different nonlinearities and had different issues with them. But really the major death knell for using the sigmoid, and it is still used in places, often usually only at the very last activation though, is that the exponent in the calculation of the sigmoid, and we've seen the formula for it previously, that exponent is expensive to calculate. And because of that, you could often have systems that could calculate very, very quickly this part of the perceptron back here, very quickly calculate this, and then be very, very slow to calculate this. And that's that's a problem that we always have to look out for when it comes to activation functions. Now, they ended up the most popular. Now, there are slight variations on this. There's the leaky rectified linear unit, and there's I've temporarily forgotten the name of it, but there's another one now that there's the one that kind of comes down and does something like that. There's the leaky one, which I'll draw maybe with a red line here, which goes like that, and then I think there's another one that kind of goes down and back up like that. So there are a few different ones of these, but we'll just look at the rectified linear unit for the moment, which is very, very simplistic. So basically, what we have is we just have a very straight line here. So straight line here, which basically says it's got a slope of 1. So 1 in equals 1 out, 2 in equals 2 out, 3 in equals 3 out, and so on. So it's linear in that range, but nothing below 0 is allowed in. Okay, now this can seem extremely simplistic, and as non-linearities go, this seems to be very, very linear. One of the other problems with it is that it's not actually, it's only piecewise differentiable. So when we need to calculate a gradient, we've got a bit of a problem at that point there, because any of these are tangents to that at that point. So we've certain problems there, but in digital systems we can kind of get away with that by just calculating the gradient before it and just after it. So the rectified linear unit is now the most popular activation function. The reason for this is that it is the most simple, but it still seems to work well in practice. Now, Alex Krizhevsky, whose name, you grow familiar with some of the important names in deep learning. Alex Krizhevsky is the guy that created what's called AlexNet. I don't think he called it AlexNet himself. I think people called it that afterwards. And AlexNet was the first deep learning solution for the ImageNet challenge, and it won in 2012, and it was streets ahead of all of the other competitors at that time, and nobody has ever won the ImageNet challenge since that time without using deep learning. So it was really the beginnings of deep learning being useful, not the beginnings of deep learning, but the beginnings of deep learning winning competitions and being useful. So I've a link to his paper there, and he describes this model. And one of the things that he shows in it is that by using ReLU instead of TANH, so he tried training with both, was that the model converged 6 times faster using ReLU than it did with TANH. Okay, now whether that was because of the calculations that it took to do TANH, or whether there was something inherent in the idea of ReLU in terms of that even if they cost the same to calculate, that ReLU would converge quicker. I can't quite remember. I don't know whether he drills down into that detail or not. But one way or the other, ReLU is very, very simple, so it's very quick to calculate, and it gives good results, particularly in terms of visual recognition, which is where these are used most often. There is also some suggestion from neuroscience that this is the most similar to what biological neurons do. But again, as I say, biological neurons, and we're not really trying to copy the brain. If we knew exactly what was going on in the brain, we might. But we might also find that, the biological brain is not necessarily the perfect system to do this with computing, and we may find better ways just by going our own way about it. So as I mentioned, there are some other ones that you'll come across as well, like the leaky rectified linear unit. One of the problems with this that they found was that if we had something down in this range here, was that once again we had that saturating gradient problem. So an input here, an input here, an input here, they would all have the same gradient associated with them. So, and it would be a 0 gradient, and we would learn nothing from those. And effectively what ended up happening was that a lot of the neurons within any neural network were effectively dead. And so the problem with that is then that you can't you can no longer use those neurons. So in order to keep the neurons just about alive, what they come up with was an idea called the leaky rectified linear unit. So if you were in the negative region, you didn't get as big a slope and you didn't get as big a gradient, but nonetheless you could creep your way back to being a useful neuron in some way. And so that's why they came up with that. That said, the standard ReLU is the most often used in most systems. Now, Nice piece of software, by the way, if you need to draw any neural networks, and they do it in this form and they do it in some other ones, this NNSVG, so you can click on that link there, and that's what I've used to draw this particular neural network. One of the things that it does is it kind of comes up with a different value for the weights, and the weights are shown as the lines here, so the thicker the line, the larger the weight, but it's just randomly generated for this. It's not, we don't have an actual network in this one. So you have an input layer, which is this. Okay, so we have our input layer, and that's connected to, so each one of these is an individual perceptron. So it's connected to all of these ones, which are connected to all of these ones, which are connected to an output. So the input layer, two hidden layers, and an output layer. How many weights do we have here? So the question is, how many weights do we have? So we've got 7 inputs plus a bias. And we've got 7 in this layer plus a bias. We've got 3 in this layer plus a bias. And then we've got this result. So we can calculate this by basically saying, well, we've got 8 there, 8 multiplied by 7. Okay, so each of those 8 has to go to each of those 7. We then have the 3. So for each of these 3, we're going to have we're going to have 8 of these. Okay, and you can add that onto the total, but you have to you're including the bias there again. And then for this one, we've basically got 1 by 3 plus the bias, and you can tot up how many you have there. The thing is that this is assuming 7 features and your bias. And if we look at something like the example that I give you there of MNIST with the handwritten characters, we've got 784 features, and then we'd have to include our bias. But the bias doesn't matter too much in terms of complexity at that stage. You can see how this would be a very, very complex system indeed. Now, these are known as dense layers or dense networks, where everything from one layer to the other layer is connected. So it is a connection. So every one of these is connected to every one of these, and then this one is connected to every one of these. They're not connected between them each other on the layer, but they are connected to every one in the other one. This is not how we end up doing most of them, by the way, although we do normally have the final few layers of a deep network as a dense, or what we sometimes call a fully connected layer. So the way that we save on weights is we use a system called convolutional neural networks, and I'll be giving over a full lecture to that next week, so we'll discuss more on that when we get there. So this is the idea of a neural network, and this is a nice little diagram that I've taken from Francois Chollet's book, Deep Learning in Python. Now, Chollet is the guy who developed the Keras library, which sits on top of TensorFlow, which is a library made by Google for doing deep learning. So he's a very influential and important guy, and this is from his textbook, which explains deep learning, but also using Python, but also obviously his Keras library. So what we have here is a network where our inputs here, input X, goes in through the different layers of the deep network, and we've got these weights obviously that get multiplied by it as we go. And what that produces is a prediction, and we call our prediction Y prime. So that's the little tick up there is the prime. Now we call it Y prime rather than Y because Y stands for our true targets, which we call our ground truth, or our labels. So we know what the input label should be with that, but our network, particularly in the beginning, could produce absolutely anything. So what we've got to do then is we've got to compare that with the true label, and we do that via what we call the loss function. So the loss function is something that's very separate from the rest of the network. And indeed, once we finish training, we no longer need the loss function. We're just going to output predictions. So the loss function gives us a loss score, and from the loss score, that gets sent to an optimizer. The optimizer would normally be something like stochastic gradient descent or something like that. But what we've got to do then is we've got to update the weights. Okay, so we need to know the gradient of each of these weights with respect to our loss function. Okay, and we're going to talk about that tonight and how we would do that as well. And then what the optimizer does is it moves a little bit in that direction for every weight in our network, and it updates our network. The hope is that at the end, when we input an X, the Y that we predict is the same as the label, or the same in as high a percentage of cases as we can get, and the percentage is going to be our training accuracy from that. Okay, so that's the overall idea, and what you really need to get a clear idea of with regard to this is, what is the difference between training and inference, and what effect does it have? So inference is the word that we use for when we just want to do a single prediction after we've trained it. So a lot of people get so hung up with training deep neural networks that they forget that the whole idea is that once it's trained, it has to go and do a job, and that job is inference. So in short, training requires both forward and back propagation, whereas inference requires only forward propagation. So what we're saying there is that to train the network, we need to go forward through the network to there, and then we need to go back through the network this way and update each of the weights. That's what happens during training. But during inference, which is once we have it trained, we just go forward through it and we come out with a prediction, and that's the job. And of course, the whole idea is that during inference, when we don't have any labels at that point, we're bringing in new data. So for training, we normally split the labeled training data into batches, with batch size, with the size of the batch being a hyperparameter. So we don't send all of the images through in one go, because we might have millions of them. So we only send a small package of them through. It could be 64 of them, 32 of them, 128 of them at a time. When we pass each batch of images through the network, at each layer, this creates a set of activations. So we're going to have sets of activations being created here at each layer as we go, which are the different representations that we've created. We have to hold on to those representations because they're going to be required for our backpropagation algorithm. So we must retain the activation data for the backpropagation part of the process, and this means the retention of quite a bit of memory. So this is the first thing that we see straight away. When it comes to training, we need to retain a lot in memory, and that restrains what we're able to do. And it also means that we generally have to have much more powerful hardware for training than we do for inference. When the images have been passed through the entire network, we must then use the final activations, which are the y prime, to compare with the labels via the cost function or the loss function. Now, when the loss is calculated, this is then back propagated through the network using what we call the backpropagation algorithm, which is a repeated use of the chain rule of differentiation to calculate the gradient of the loss or the cost function with respect to each individual weight. Now we're going to do examples of that at the end of the lecture, so hold on for that. Now this needs the upstream gradient. In other words, the gradient at each later part of the network needs to be brought back down through the thing. And this is where I mentioned earlier that if that gradient gets put to 0 at any point, that can mean that none of the gradients from then on actually are able to propagate down. So this needs the upstream gradient that has been propagated down to the weight and the value of the activation at that point from during the forward propagation. So you need both of those pieces of information in order to calculate the next gradient going down the way, and that's why you need to retain all the activations as you went. So once the backpropagation is complete, we can then make a change to each weight. So once we know the gradient at each individual weight along the way, we can then make our small little alpha learning rate change at that point to each individual weight for it to go in the correct direction. So it means calculating the gradient for, if you've got 1,000,000 weights, you've got to calculate the gradient at each individual weight's position. So we move in that direction via the magnitude of the change is dependent on the magnitude of the gradient and on the learning rate. The two of them multiply by each other. Once each weight has been updated, we can progress to the next batch of images and go through the whole process again. Now, I mentioned gradient descent here is the mechanism that we go down. Strictly speaking, if we only put a batch of images through, we don't know the gradient for the entire epoch of images, right? We would call it an epoch is basically when we go through all of the images. But the entire images in the dataset or in the training dataset haven't gone through here. So what we're hoping is that if we've randomly selected the batch of images from the full training set, that it will represent the loss that's associated with the whole training set. That's not necessarily going to be the case, and you're going to have a bit of randomness in there, and that randomness is called stochasticity, and that's why you'll hear this algorithm called stochastic gradient descent, where we're actually descending the gradient, but we're doing it in a kind of random way. So you're going to see this jumping up and down a little bit, but only a little bit. In general, you should see this downward trend with gradient descent or with stochastic gradient descent, and if you don't, you generally know that something's going wrong. So we continue through the batches until all images have been seen, and this is known as an epoch. and will continue for as many epochs as is necessary to converge. We may use a validation set every now and then. So when we split our data into training and validation and test, we may use a validation set every few epochs to test the generalization of the network. In other words, to see how well is it generalized. And we'll normally retain copies of the weights that we have learned at each individual point. So while the weights change, we might like to keep a copy at particular points in the training. And these are useful because if we find that we've overtrained in some way by checking with our validation set, we can always step back to using those weights. Okay, so that's important. They're known as a weights checkpoint. So we may use the validation set to every few epochs to test the generalization of the network, and we'll normally retain copies of the weights in memory every kind of set number of epochs, so that we can step back if further training has made the situation worse. So, for example, if we start to see overfitting occur, we know that the training rate might still be going down, but the validation is starting to go back up again. We might want to go back to where it leveled out. All of this requires a lot of memory and compute power, and is generally carried out on graphics processing units, or GPUs, that are very energy hungry. Okay, so the ones that are in my machine they're using about 180 to 200 watts. That's not something you can put in an autonomous vehicle, because you just simply don't have the energy to give it. And so generally they like to keep the energy used by the entire system for recognition. They like to keep it under 100 watts. And I think the Tesla's latest one is in around 70 something watts, or the low 70s. Now, for inference, once you've done your training, while we can send a batch of images through, but we often only send a single image through at a time. It really depends on whether we're dealing with video or we're dealing with individual images, because we might just want to get a single classification done, or we might want to be continually classifying. And we can put a full batch through if that we want to do it that way either. It depends on the setup. In either case, we only need to retain the memory for a set of activations for long enough for them to be used by the next layer of the network. So as we're passing through the network, we learn a set of we have a set of activations. They're the input to the next layer. Once they're input to the next layer, we no longer need them at inference, because they're of no use to us. We're not calculating a new gradient or anything at that point. Now, that allows for a smaller memory footprint, but it also allows for the possibility of you doing something like pipelining, where you have an image coming in, and once it's gone through that layer, you could have a new image coming into the next layer and have them passing through the network in that way. It really depends on what it is that what your priorities are in terms of energy usage and memory usage and so on. But you have a lot more options available to you with inference than you have with training. So this allows for a smaller memory footprint, or it allows for pipelining, where new images are coming into a layer as others are leaving, and so on. So you have lots of different options there. In the first case, we can lower the memory and compute usage. In the second, we can use the same memory but have a higher throughput. In either case, once an output has been reached, this value called the prediction is used and then discarded. There is no label at inference time, so there's no comparing to a cost function or anything like that. There's no calculation of that, and there's no backpropagation necessary to calculate. So this means that in autonomous vehicles, the hardware can be much less powerful and have a smaller memory footprint, and this saves energy usage and cost. And one of the other things that I didn't mention here, but they do often do, is they'll often re-quantize the weights. So where the weights might have been floating point numbers in your original train network, they might turn them into integers, or they might decide, well, we're going to go from 16-bit down to 8-bit in order to try and get that processing, amount to number of calculations down, or just to save energy, or for whatever it might be. Maybe it's memory, one way or the other. So they might say, well, okay, you've trained your network now, but we're going to accept a lower accuracy, and we're going to do that by re-quantizing the weights. So there's lots of different options available to you once you go from training over to inference. Now, this is a slide that hopefully you recognize. It's from the very first set of lectures, but it's all about representations again. So ask yourself the following question: how would I represent the number 13? And you see that we have lots of these different representations, and some are more useful than others depending on the different sort of situations that we want to use them in. So what a lot of computer vision was, and this also goes for natural language processing, of course, as well, and some other things, but in particular we're interested in kind of the computer vision end of things. What we would do is we would via some hunch or prior knowledge about the domain and the data format, we would engineer different representations that we felt we could use easier. And that might be because we developed an algorithm to use them, or it might be that we would develop the representations so far that we could then put them into a relatively simple machine learning algorithm that could then work with them from there. So you can imagine something like logistic regression. It mightn't be able to work with straight pixel values, but if we change them into some other representation, then we might be able to put them into the simple logistic regression, and it could work from there, or SVM, or whatever else it might be. So this was the idea of feature engineering, or engineering engineered features, and by engineered we meant that a human came up with them. So it involves using prior knowledge about the domain, the data format, the machine learning algorithm that you're trying to put them into, and so on. And what we do is we hard code, i.e. not learn, but hard code some transformations to the data before presenting it to a machine learning model. This makes it easier for the model to learn, but this is because we are doing some of the learning for it. Okay, so we're doing a little bit of that ahead of time. Now this is reasonable because simple models cannot be expected to learn from any sort of arbitrary data. They're normally set up to work from particular types of data. So we have an example here, and again this example is from Francois Chalet's book, but actually what I have on the next slide here is a picture of a manufacturing vision system that we have in one of the labs here in IT Sligo, and you can see here that what we have is we've got a camera system here, and that camera is looking down like that, and it can see this. This is actually some sort of a hygrometer or something here, a little bit like a watch face. And what it has to do is this robot arm has to come along, pick that up and put it into a particular, I happen to picture the setup, but it has to put it in at a particular orientation of this, okay? But the same idea here, how would it actually go about figuring that out? So if we just use the raw pixels here, so just the grey values or black and white values here, could we figure out what time we have on the clocks here? So we can see how the raw pixels would require a complex model to determine the time, because it'd have to see an awful lot of different times in order to be able to figure it out. We'd need a lot of samples. And it'd be, again, a very non-linear problem. Now, simple edge detection algorithms could calculate the better features perfectly. So we could find the big long edges here, and we could write in the coordinates of them here, and you can see the same sort of thing going on here. Or we find the beginning and the end of the longest line. So we might find the longest two lines. So we're not too concerned about figuring the length of these lines, but we are worried about the length of these lines and so on, and how long they are and what direction they're pointed in. And from that, we might want to decide, well, we're going to go from the Cartesian coordinates to something that's a bit of a nicer representation, which is we want to find out what the angle that it's creating. Because if we know the angle, then it's a relatively simple thing to change that to figuring out what time it is. Indeed, we wouldn't really need a machine learning algorithm from there. We could literally just have an algorithm to work it from there. So from there, we could represent these directly into polar form to give us angles and lengths, so we can determine the angle of the hour hand and the minute hand. And from there, we could have a mathematical equation or a lookup table or whatever it might be. But the thing is, even young children can figure out what time it is on a clock, and they're certainly not going and figuring out this sort of things. They're not looking at edges. They're not calculating angles or anything like that in order to do what they're trying to do. So can we have a system that would just learn that from scratch? So we could try getting our machine learning algorithm to discover not just the mapping from the engineered representation to the output, but also learn to create appropriate intermediate representations itself. Now you might say, well, can we not just go straight from one to the other? The problem is that often it's difficult to make this representation change in just one jump. So our systems can find it difficult to go right from there to the end, but they can make small jumps along the way. And the question is, can we then learn these intermediate representations rather than us having to figure them out for it? So this is where the deep learning comes in. So the deep in deep learning refers to the number of levels, and each level tries to change the representation in some way, so that the more levels we have, the more the easier each new representation should become for us to deal with. And this is until we can eventually put something like a simple SVM or logistic regression classifier on the top of it, and you can more or less interchange which one of them you use. You know, it's not that fussy. You can get it to work with any of those simple machine learning algorithms at the end, once you've changed it into a nice representation via these deep neural networks. So you'll normally find that the end of these networks have one of the simpler machine learning classifiers on the end of them. And that's why we use this word, your favorite, okay? Because some people like to work with different ones than others. These learned representations can often result in better performance than the hand-engineered representations. So often the lower level features are universally useful for similar tasks, and indeed that's something that we're going to do. It's what I'm planning for your second assignment, is to do some of this transfer learning. And the reason for that is that you don't have to have very expensive hardware to do it. So this means that we can adapt to new tasks with relative ease by only retraining part of the network. So what we find is that whatever representations it learns early on, they tend to be universally useful. Learning representations takes longer and requires a much more complex model than when we supply the hand-engineered features. And that's because effectively, if we supply the hand-engineered features, what we're doing is we're standing at, the idea of standing on the shoulders of giants. You're standing it on what you've already worked out, and you're asking it to learn less. You're just asking it to learn the last little bit. So that can mean that a process that might have only taken minutes can now take hours, or what used to take hours could now take days or weeks. However, if you consider the equivalent of learning, of figuring out hand-engineered features where we figure them out, this is a complex task which requires a lot of human ingenuity and time. And you can think of that in terms of decades, and that's for a community of researchers. So thousands of researchers can take decades to come up with these engineered features. The reason that we do use them is that we've already figured them out and they work quite well. And most importantly, we know what they do. Whereas the learned features, we don't quite know what they're doing or why they're doing it. And this brings us on to the idea of causal reasoning, which, as I said, is something that will be a theme throughout our machine learning, and you can expect it to be a theme throughout the rest of machine learning and deep learning's days. With hand-engineered features, there's a direct path of causal reasoning for any input to output. Because we've engineered it, we've had to come up with the theory behind it, and we've explained how it works, and therefore we know if we get a certain input that we're going to get a certain output. What this means is that we are able to follow the line of reasoning that takes us from the raw data to the decision or the result. So with a deep learning system, this is not so easy, and in some cases it's borderline impossible with our current knowledge. So this is a big area I say it's a big area of research. Unfortunately, researchers still want to just get up the percentages, okay? And they're not as interested in exactly how it's doing what it's doing. And we really should be more interested in how it's doing what it's doing, because that's probably more important than what we just call here state of the art. And you're going to see that change in research in the next number of years, because it's no longer good enough to just get a slightly better percentage if we don't know why. If we consider the example of System A achieves 80% accuracy on a task, and we have causal reasoning for it, but System B achieves better. It achieves 85% accuracy on a task, and it doesn't have causal reasoning. The question is, which is better? Okay, now which is better really depends on what we want. But if you're dealing, with something like voice to text, where if it makes a small mistake, or predictive text or something like that, if it makes a small mistake, that's not really the end of the world. You might send a slightly wrong message, or you'll probably have to go and change it. And in that case, you might go, well, I'd like the 5% extra accuracy. I'm not too concerned about how it's figuring out what it's doing. I'm more concerned with the accuracy. That's fine. But if you're dealing with a mission critical system, where when something wrong happens, so when it makes a mistake, the situation can be catastrophic. And in those sort of situations, obviously if it's happening 15% of the time, that you're probably not going to use that for a mission critical system at all. But even if it's 99.999% of the time that it gets it right, if that's 0.0001% of the time, which is still going to happen quite a bit, if that results in something catastrophic, like a car accident, where people are injured or killed, then we have, we're going to spend an awful lot of time on that particular edge case. So humans like knowing why something happens. And you're probably aware that Uber had an accident a number of years ago with an autonomous vehicle. They're still discussing that and still interrogating that to this day. Now, there has been tens of thousands, probably more than 100,000 deaths on the roads worldwide since that. They're not getting the same level of investigation, because what normally happens is they determine quite quickly human error. And once we have human error, we have somebody to blame, and that human was only driving that car. But if we have a deep learning system that's making decisions and it makes an error, and we just say deep learning error, well, that deep learning network is in everybody's car, or at least in everybody who has that same make of car. Now we get panicky. Now the same sort of thing can happen to us. So if we can't tell them the benefit of the extra accuracy, just having the benefit of the extra accuracy may not convince them to adopt a system or product. And indeed, it can lose their confidence when they see an accident occur. So when it comes to mission critical systems, we cannot simply say that a system A is correct more often than system B if when system A fails, the result is catastrophic. Okay, it's just not really an option. So causal reasoning is going to become a bigger and a bigger issue for us. So what can we reason from learned features? So can we in some way do some causal reasoning on learned features? And we can, but it's certainly not as easy because we don't have the theoretical underpinnings behind it. So sometimes these learned features, if we go in and interrogate them and look at them, they look like the named hand-engineered filters and features from the literature that we developed over the years. So if they look the same as those, we figure, oh, it's realized that this exact filter that we also realized does this particular job, and therefore we can make sense of it. So examples like Laplacian filters, Sobel, Gabor filters, we see those pop up, similar ones to those pop up within inside deep learning networks, and it's basically finding that at a particular layer of representation, it's useful to use this filter. But more often they do not, and we don't know why they've learned what the filters that they have. Okay, it doesn't necessarily make sense to us. It may not even be reasonable for us to expect that a machine, which is not a human, is going to learn features that make sense to humans. That may be an actual unreasonable expectation for us to have. But you can expect that trying to infer some sort of causal reasoning with deep learning will be a major area for research into the foreseeable future. And certainly it can be helpful to look at those features, see if we can make some theoretical underpinnings from them, and then turn them into hand-engineered features. In other words, get the system to learn good features, which we can then figure out might be a good place to look for hand-engineered features. Let's go back to the training and the idea of gradient descent. We've seen in the various machine learning methods that we can use gradient descent to descend the loss function. To do this, we needed to determine the derivative of the loss function with respect to each weight, and then make small moves, which are alpha, in a downward direction at each weight. This is achievable with relatively simple models like logistic regression or SVM, but what do we do with complex multi-layer perceptron models like neural networks? There are many complex designs of these different networks. They have millions of parameters, some of them, and the question is, must we determine the derivative of the loss function to each one of those weights? And the answer to that is both yes and no. No, we don't have to do it on paper, but yes, we do have to do it. So we need to find mechanisms whereby we can do it in a computational manner. That's what the backpropagation algorithm is, but before we do that, we need to look at the other way of doing it, which is numerical gradient. And actually, this is how a lot of people think that the system works, but it's generally not. So we can try this by numerical methods. And the idea is we make a small move in terms of our predictions. So we decide to move our weights in some manner. And in making that move, we see whether things go up or down in terms of our loss function. Okay. And we do this at each different point within the network. So basically what we do is we see where the loss is going with regard to it. And there are a few different ways of doing this. You can just make a single move, or you can normally, it's better to have a balanced where you look at the move before and the move afterwards. And you calculate this. So you calculate it by finite methods. The idea here is that we can make some changes by a small amount and determine the change between two states for every weight in the network using the above formula. This then will tell us the approximate gradient, and that's approximate gradient for that change. We can then make changes that descend the gradient and recalculate the new gradient after each step by the same method. Okay, the problem with this is very, very computationally intensive. Doesn't always work perfectly. Now the other way is analytic gradient, which is the idea of you actually working it out on paper. So like the methods we used for the less complex machine learning method, we must come up with the analytic gradient for the loss function with respect to every weight in the network. So with the simpler methods, what we did was we could design an analytic gradient and we could literally just go to the very bottom of that. That's not really an option with these very large networks because we can't calculate the full function for the entire network, but we can calculate the gradient at each individual part with respect to the loss. So this sounds impossible for the millions of parameters, but thanks to an algorithm called backpropagation, it can be achieved by a computer algorithm. And we'll detail the backpropagation algorithm in a moment, but first we need to determine the relative merits of using analytic gradient versus numerical gradient. Now, numerical gradient is slow to execute, and it's only approximate. It is, however, easy to code, so there is little chance for bugs in the code. Analytic gradient is fast to execute and it's exact. Okay, so it's much better if we can do it. The difficulty is that it's difficult to derive, so we might get our maths wrong. It's difficult to code, then even if we get our maths right, did we incorporate that into our code correctly? And this makes it error prone. So bugs in code, which are a fact of life, are something that you need to take into account. If I do this, it's not just hard work. Am I going to introduce a bug? And how am I going to find that bug? How do I even know that the bug exists? That's really part of the problem. So in practice, we do our best to derive the analytic gradient and then code it. We also code the numerical gradient. So we code both of them. And we compare the two answers when we test our implementation. If they're different, we have a problem. If they're the same, if they're consistent, what we then do is we remove the code for the numerical gradient because we basically say we don't need to run that. Our analytic gradient is working correctly and it's the fast one. So it's a bit like removing debugging code from your program. So if they're consistent, won't be exactly the same, but they should not be wildly different. Then we remove the numerical gradient code and we train our model. If they're not consistent, we go back to deriving and coding. Now, in practice, in modern frameworks, we actually don't do both in most cases, right? Even though maybe we should, but with recent deep learning frameworks, most of the blocks that we require have already been derived and coded, and we simply need to use the library. And the truth is that, like many functions, library functions, if we were to write that library function ourselves, it would take us a lot of work. We might do a slightly better job, but it's unlikely. And the third thing is the chances of us introducing a bug are quite high. Same here. If we have a deep learning framework which has implemented that particular block already, it does not make sense for us to reintroduce that because the chances of reproduce that, the chances are we're going to introduce a bug. Instead, we should use that block, and that block normally has the gradient already, the analytic gradient already calculated. Assuming that everybody's used that block quite a bit, we've ironed out any of the bugs that are in it. However, at the cutting edge, we may have to use something like a bespoke loss or cause function or a block that we must write the analytic gradient function for. So it's good to be able to verify that, at least that small bit, with the numerical gradient. So this is not something that has completely gone out with new modern frameworks. We still normally have to do something at the edge where we're introducing something, some new system, and that's where we can kind of add value. So this brings us on to the backpropagation algorithm. This employs the chain rule of differentiation. And the chain rule of differentiation, how many of you remember that at least there was a chain rule of differentiation? How many of maybe just let me know there. It's a while, I'm sure, since many of you have done differentiation. So you do remember it. Okay. Yeah, it's a long time ago. Now the thing was that when you did the chain rule of differentiation, what you did was you had a function of a function of a function would normally happen, and what you did was you firstly got the derivative of the function as a whole. So let's say it was the cosine of let's say it was cosine of x squared or something like that, you'd firstly get the derivative of the cosine of x squared. That would give you a derivative of that, and then you multiply it by the function on the inside, which was the x squared, which would go down to 2x, and you multiply it by that. Now, the thing that we have in something like a neural network is we have a function of a function of a function of a function going all the way through all our layers. And so there's millions of these, but it's really just the same operation over and over again. Get the derivative, multiply that by the derivative of the next part, and then multiply that by the derivative of the next part, and it works its way down. What I've done is I've come up with a very simple example here, and this is normally most courses will do a very simple example like this. If I get time during the week, I'll do a more complex one, and I'll put that up as a separate recording, just so that you see it. And the reason I want to show a more complex one is that this is of limited use when we do this particular one here, because one of the things with it is that it's a function, but there's actually no weights in it. And of course, the main thing that we want to get the derivative of with respect to is weights, so that we can then modify them. We're going to get derivatives just with respect to values. There are situations in which you would get derivatives with respect to the original values of the image, and that's if you wanted to change the image in some way. It's used in artistic settings, and I'm actually just going to show you an example of that, which maybe you've wondered about or not. This image here, that's on the very front of the notes, is using this idea here. We started with a pre-trained network. I can't remember which one it was. I have a feeling it was Inception that I used, and it's already been trained on something like ImageNet. And what we then do is we start with an image. I've started with an image of Ben Bulben, which, if you've not been to Sligo, it's a mountain here in Sligo. And what I did was I get one of the filters within one of the activations within the network. I get everything with respect to it, and so I change my image to up the to basically make that activation higher. They call it dreaming, but it's maybe a bit more like hallucinating, in that we want to fire that neuron like crazy, and we change our image in order to fire that neuron like crazy. So as you can see, the particular neuron that I was using, it liked this particular this sort of pattern that we see here, these swirly patterns, but also it looks like it's kind of like some sort of whatever you do call it, crochet, or what, I'm not sure what the word for that is, where they sew in the sort of things into it. It looks a bit like that as a result. So that's an example where you could use that to change the image, but as I say, in the majority of cases what we're doing is we want to change the weights. I've just come up with a very simple activation function here, and that's what we're going to do. So the function is as follows. We take three parameters, x1, x2, and x3. We add x1 and x2 together, and then we multiply them by x3. So the idea here is that we've got the multiply function and we've got the addition function, and we have to get our derivatives around that. So we've got a function of a function here. So we're going to start with some values, and I've a few notes written down in front of me to make sure I don't go wrong. We're going to set x1 equal to 3. x2, we're going to set it equal to 2. And x3, we're going to set that equal to -2. Again, I've just made up these numbers arbitrarily. So I'm going to write those in. I'm going to write 3 there, 2 there, and -2 here. Our first thing we have to do is do our forward propagation. So we have to send these things through the network. Very, very simple network here. So does anyone want to give a guess at... By the way, I've given it an extra name just to this section here so that we have a name for that. What will be the result? So what result will I get there? Does anyone want to just calculate that quickly and see what you get? Okay, so Jerry's been the quickest off the mark. So 3 and 2 added together is going to give me a value of, is going to be equal to 5. And 5 is going to be multiplied by -2, and that's going to give me -10 as an output. Okay, so very good. So that's correct. Now, the first thing to say is that if we were to get something like df, I should really, by the way, be doing these as partial differentiations. Okay, so forgive me if they don't come quite out there. df is just a value of 1, right? So I'll just put that number there just so that we remember it, right? So what we want to do is we want to calculate the gradient at each different point along the way. Okay, so let's find out what is my gradient going to be. What is my gradient here going to be with respect to A? So we would do that with something like df dA. Okay. Now, well, what do we have here? We basically have, if we look at A. Sorry, what am I doing this correctly? Right. Yeah. So F. We'll write down F first of all. Is what I want to do. I'm trying to see how best to use the space that I've given myself. F is equal to, we said that F was equal to this, but actually what I'm going to say is that F is equal to A multiplied by x3. Okay, so we're going to use that, and I'm so that my A now is a function that we're going to get later on. And if I want to get F, the derivative of F with respect to A, does anyone want to figure out what the answer would be? If I got the derivative of F with respect to A there. Yeah, and Ratko is correct. Here's the thing, right? And this is the thing about differentiation. This is a bit like saying I have 2x and I want to get the derivative with respect to x. It's just going to be 2. Okay, so whatever we have there that isn't x, whatever we have that isn't x is what I'm going to be left with. So whatever we have that isn't A is our number that's on the front, which is going to be x3 here. Okay, so that's the idea there. And what that basically means is that our derivative there is going to be x3, and we know that x3 was a value of -2, so I'm going to write that up there as being -2. Okay, so this is my gradient coming back to it. And I said that what we want to do is we want to keep our activations and we want to keep our local gradient as well, because those two pieces of information are going to be used in order to determine the different parts of what we're going to do to work our way back. All right, what would be the gradient with respect to x3 now is the question. So maybe I'll just write that down. So df dA is going to be x3. Now, what's df dx3 going to be? Anyone want to take a guess at that? Yeah, so Radko said it's A, and of course we know the value of A there, it's 5. So we're going to put that down there as 5 is going to be my gradient back there. So what that basically says is that if I want to go and, you know, up my answer here, what I want to do is I have a gradient with respect to my number here. So we know what the gradient is, and we then decide with regard to alpha how far I'm going to move that with regard to the two of them. Okay, so you can see that what's happened with the multiplication is in effect these two things have swapped their numbers. Okay, so whatever number came in here got swapped and is now the gradient of this one, and whatever number came in here is now swapped and becomes the gradient of that. And that's what happens in a multiplication situation. Okay, now so we'll maybe just write that one down, and that's going to be A. Now my next question then is how do we get the something like df dx1? And this is where we would have to use the chain rule. We would have to say that we have to get df dA, and we would multiply that by dA dx1. Okay, so that's what occurs in that. Now we have already calculated df dA, if you recall, so we'll write that we have calculated it as being x3, and we know that x3 is a value of -2. Okay, just watch that, it's not the 5. I nearly went and put the 5 myself, but it's the original value of x3, which is -2. dA dx1. Okay, so firstly, what is A? we need to write down what A is, and A is equal to x1 plus x2. So does anyone want to figure out what is dA dx1 if A is equal to x1 plus x2? Yep. Okay, so do you see where Ratko has got that from? So obviously Ratko knows his calculus, which is good. Okay, so the point here is that if we can basically split these up into their two parts, x1 and x2. So dA dx1, if it's just x1, well, that's just like saying dy dx if you just have a value of x and you're just going to get a value 1. So that comes out as a 1 there for that. x2 is basically like just having, if we had something like y equals 3 and we get dy dx, well, we have no x in there, so that's going to just come out as 0. So we're going to add 0 onto that, okay, because it's just a constant value. So that's going to come out as 1. So we'll write that up there. And what about x2? What do you reckon that one is going to be? Sorry, I've written that wrong. I've forgotten something. What did I meant to put that here, that 1 there, and we multiply these by each other, so I get minus 2. Okay, so that should be minus 2 there, and that's important. We need to take our upstream gradient that's on its way down, and then use the local gradient in order to figure out what the gradient is going to be at each point. So can you figure out from there what's going to happen with my value? What's going to be my gradient at x2? So df dx2. And by the way, I'm only showing you this in the first case where I do the df dA multiplied by dA dx2, because I don't really need to do this part here on each occasion. Okay, so we can see that the same thing is going to happen. We're going to have a 1 again. It's just going to be 0 plus 1 in this case. So that's going to be a 1. The df dA is still minus 2, and so when we multiply these by each other, we should get minus 2 as well, and that minus 2 ends up there. Okay, so this is the backpropagation algorithm, and the idea is obviously, and I'll show you, as I say, I'll try and do maybe a recording of a slightly more complex version. It's just it would take slightly too long if I was to do it during the lecture here. What would normally happen is we would have our x1 and we'd be multiplying this by a w here, and the two would get multiplied in. So we'd have a little bit like what we have up here. And then of course we might go through something like a sigmoid function or something like that. And we then get the gradient with respect to those weights, and then we make our calculation of the change to the weights. The important point is that at each different point, all we need to know is what's the gradient coming from upstream with what's the current what's the current function that we're dealing with. And once we know that, we just multiply that, because this has included everything that got multiplied into it beforehand. You wouldn't do this on paper, of course, but you do this as an algorithm in your computer program where it works its way back. And if you have to add in some new block yourself, then you do have to include a function for the gradient, so that the system then knows how to calculate the gradient going through that. And one last thing to mention is, if we ended up with a gradient of 0 somewhere, well, then that gets multiplied everything else by 0 down the road, and that's called the vanishing gradient problem. And that can be a bit of an issue with regard to deep networks, because at some point along the way you make the gradient to 0, and that chokes off the gradient getting through the rest of the network down the way, for anything that's a kind of a child of that going down the way. Okay, I'm going to leave it at that tonight, guys. So thank you for your attention, and if you have any questions, obviously just put them on the forum, and I'll try and answer them there.